Hi guys, I'm Priscilla, and if you didn't know, your tan line is showing. And that was a corny pun. Get ready for more of them because I'm sure they'll be dispersed throughout the video. Anyway, I've decided, or rather it's been decided for me, thanks to Snowval, that I'm going to make a video to kind of help anybody out that needs some help on section 910, Taylor and MacLaurin series. So maybe you're familiar with the section, maybe you just want to brush up on it, AP tests are coming around. So regardless of what your reasoning is, I'm here to help and hopefully you gain something from this video. Alright, so let's start by defining what a Taylor series and a MacLaurin series is. The very formal definition says if a function f has derivatives of all orders at x equals c, then the series, as shown over here, f raised to some n of c over n factorial times x minus c raised to some n is equal to f of c plus f prime of c times x minus c plus it goes on, but again it goes back to the form f raised to some n at c over n factorial times x minus c raised to some n. As you continue deriving, obviously n will continue to increase. And so when you see a series in this format, you will definitely, or you should, recognize it as a Taylor series for f of x at c. If c is equal to 0, however, then the series is actually considered a MacLaurin series. Wait, what? Love you, Merlin. If that seemed a little complicated, I'll make it really simple. We'll play a game called Whose Series Is It Anyway? It's a game where the rules are made up, but the points do matter, particularly the center. Alright, so a series is centered at C. Is it equal to 0? Well, yes. MacLaurin series. No. Taylor series. It's really that simple. A MacLaurin series is a type of Taylor series. It's just centered at 0. So that's a quick little tip of remembering that. Alright guys, so I thought we would do an example now that we know what a Taylor series is and its definition. So this is on page 687 of our textbook. It's number 3. And what it asked was to use the definition of a Taylor series in order to solve this. So what it gave us was f of x is equal to cosine x, and it told us that it was centered at pi over 4. So because it's not centered at 0, we know that it's a Taylor series automatically. That was, part of our little game. Centered at 0, MacLaurin, not centered at 0, Taylor series. So what I did first was I made this little chart right here. This chart was all the derivatives, or at least the first 3 derivatives of cosine x right here. Just because we know that we're going to use that when we actually start doing that. So I like to make a little chart so that I can keep track of my derivatives. The next thing I did was I plugged into my derivatives. We know that it's centered at pi over 4. So for the first derivative, for the first just cosine, it's cosine of pi over 4, which is radical 2 over 2. The next we had negative sine pi over 4, which gave us negative radical 2 over 2, negative cosine and sine, and so forth. And so I just got the values for these actual, for our derivatives. And again, that'll be that'll be useful later and when it comes to actually simplifying this. So next step, part 3, was simplifying. And so what I did was I wrote out my equation. Cosine x is equal to, wrong way, f raised to the n of c. C we know is pi over 4 times x minus c, again pi over 4, raised to some n over n factorial. So simplified, we'd get radical 2 times 1 minus x minus pi over 4 minus x minus pi over 4 squared over the factorial of 2. Where that came from was just, again, our original function f of c plus f prime of c times x minus c plus f double prime of c, x minus c squared over the factorial of 2. And then, once you actually plug it in, it's cosine pi over 4 plus, though it's negative sine, so actually it'd be negative, negative sign, again, plug in your c, pi over 4, x minus c, that should be a pi over 4, plus, again, you're going to have a negative derivative, so it should be negative pi over 4 x minus c squared over the factorial of 2. So when I simplified, I pulled out our radical 2 over 2 only because it would be the same for all of the derivatives. And I just, wanted to clean it up a bit and make it simple. Obviously, this can go on for a very long time, or at least however much as you want it to go, but I stopped after the second derivative. So, hope you guys followed that example. So, positive reinforcement. You guys have sat through about 5 minutes of me talking, and I think it's wonderful. So I think everybody deserves a round of applause. And, hopefully you'll stay with me for another 10 minutes. All right, let's get back to work. Alright guys, so I wanted to touch up on the convergence of Taylor series. Now with series you will hear convergence and converging and diverging a million times. You will also see it in theaters. Anyway, so basically to find out if a Taylor series converges, we have to look at theorem arbitrary number. Which states that if the limit as n approaches infinity of your remainder is equal to 0 for all x in the interval I, then the Taylor series for f converges n equals f of x. Again, f of x is equal to your summation, f to some nth power of c over n factorial times x minus c to the nth power. What this says in more, layman's term is, in other words, the power series form with Taylor coefficients a sub n equal to f raised to an n of c over n factorial. That converges to the function from which it was derived at the exact values for which the remainder approaches 0 as n approaches infinity. So Taylor coefficients converge to the function from which they were derived as n approaches infinity and the remainder equals 0. Moral of the story is to infinity and beyond. Knock knock. Who's there? Well, your good friend Binomial Series. Nobody's home. Alright, I feel kind of bad for just leaving Binomial Series at the door. So, just one more, guys, bear with me. This series, the binomial series, comes in the function form of f of x is equal to 1 plus x raised to the k. Much like in the things that we've been doing, you'll find that in this example, it's a lot like the Taylor series and the MacLaurin series. In fact, in the example we're going to do, it's asking you to find the MacLaurin series given the binomial series. They're very much similar. The process is all pretty much the same. It just comes in a different format. So that's really the only thing you need to remember, is that binomial comes in the f of x is equal to 1 plus x raised to the k. It's a special k because it's not an n. So what I have here is my example. And so the directions were find the MacLaurin series for f of x is equal to 1 plus x raised to the k. So the first thing I did over here is I differentiated. And I differentiated through chain rule like you would do with anything else. We don't have any actual numbers, but I'm pretty sure everybody's familiar with chain rule. So our f prime would be k times 1 plus x raised to the k minus 1, f double prime k times k minus 1 times 1 plus x raised to the k minus 2, and so on. The next thing I did was I plugged in 0. And the reason for doing this is because it is a MacLaurin series, which means it's centered at 0. So I just plugged in 0 for our x here, and we start getting our coefficients, our coefficients that we'll have in our answer. So for f of 0, we get 1. When we plug in 0 for f prime, we get k. For f double prime, we get k times k minus 1. And so in our answer, what we're going to do is we're going to do pretty much what we've been doing, like I said we were going to do. And so we have our answers here. So we have our 1 right there, plus our k times our x, which was what we got from setting the derivative, or not setting the derivative, but plugging 0 into our first derivative times our x. The reason we don't have a c, because it's centered at 0, so it's just x. Again, for our second, we do what we got for our second derivative when we plugged in 0 for x and then multiplied it by x squared over the factorial of 2, and so forth. And we're going to get the generic version as we did with most things at the end. The k times k minus 1, etc. K minus n plus 1, I don't know if you can see that there, raised to the x to some n over n factorial. So again, very much similar to what we've been doing, only difference is formatting of this series. Alrighty guys, so my last tidbit for you today is something that's pretty self-explanatory, however I am going to explain it to you. You're welcome. But it is the multiplication and division of the almighty power series. Yes, not as intimidating as it sounds or looks. In fact, it's just like multiplying anything that you normally multiply. Polynomials, whatever you're into. I don't know. I'm digging these series, so let's continue. This example was found in the book on 687. It's number 41, and it says, find the MacLaurin series through multiplication. So the function they gave us was x times sine x. Now, x is pretty standard. It's not a series. It's just, at this point, a constant variable. And then here's the series for sine x. I didn't explicitly write it out just for time's sake, but there is a list that if you'd like to look up, it's a basic list of just simple things, trig, lns, exponentials, just things that you might want to know off the top of your head in the event that you are doing series a lot, or just in the event that you're doing any kind of series. But I'll explain this real quick. So because it is a MacLaurin series, we know that it's centered at 0, so, you know, as we've been following the format, f of c plus f, or f prime, x minus c, plus f double prime, x minus c raised squared over 2 factorial, etc. So in doing this, I didn't explicitly write it out, but the derivative of sine is cosine, and the cosine of 0 is going to give you 1. So we just have our x here. We don't have anything over a 2 factorial, only because the derivative of cosine is negative sine x. And because it's negative sine x at 0 would give you 0. So we don't actually have anything here, but to continue on, negative sine x would then be negative cosine x, and negative cosine x again would give you negative 1, which is why our sign here is negative. And that would be our third derivative, which means our x would be cubed, and it would be over a factorial of 3. Again, we don't have a 4 because it would alternate into a sign again, but we do have a 5, and it's positive again. We would go into our fourth derivative would be sine, so again our fifth derivative would be positive cosine, again giving us a positive 1 as our answer and giving us what we have here, and so on and so forth. So what I then did was I distributed the x across the series of sine, or what we got for that, and then so you end up with x squared minus x fourth over 3 factorial plus x to the 6th over the factorial of 5. And again, you just have to analyze this and look at it. You know that your signs are alternating, so you know that you're going to have some sort of 1 raised or negative 1 raised to an n. You just, you look at your exponents for x, and then you look at your denominators and how the factorials are changing, and it then ends up looking like this very pretentious math equation that I just poorly circled with my finger. And that's all the time we have for today. A big thanks for all of you watching. A big thanks to my stepmom who brought me Dunkin' Donuts while I was doing this. And to Miss Novell, I wouldn't have done it without you. I genuinely would not have done this without you. So thank you. Bye guys.